Hey everybody, it's March 7th, 2022. This is the week of the midterms for stats. Intro to stats at College of Sequoias. We just finished studying up everything that was on the midterm. I'm going to start chapter 4. We're going to do some of chapter 4 today, and then we'll just do a quick recap of some of the stuff you need to know for the midterm that starts on Wednesday. But let me get chapter 4 started. That way we don't fall behind. So chapter 4 is on linear regression. And to do that, we kind of need to remind everybody how graphing works. Chapter 4's got a lot of graphing in it. So we've got graphing, we've got units like this. This upper vertical line is y, this right line is x. And like it goes positive this way, negative that way, and positive up and negative down. And so, and we write things in coordinates x comma y. And so if I go over 1, 2, 3, and then up 4. This point, my x value is 3, my y value is 4, and we write that as 3, 4. If we go left, it's negative movement. 1, 2, 3, 4, 5. And if I don't go up or down, I stay on this axis right here. X is -5, we went left. Y didn't change, so it's 0. This point is -5, 0. And or we could go down, we could do -5, or we could also go down 2. And now we've got x equals -5, y equals -2. And this is -5, -2. So we write our x values first and then our y values second. And then usually if we have like a line, let's see if I got it set up to be a good line. No, not really. Not with the points I've got. So I could make some new points real quick. So lines in mathematics are straight. Anything else is called a curve. And this chapter is on linear regression, so we're going to be dealing with straight lines. There's a couple ways to write the equations of a straight line. We always, since this is along x and y, we want to reference x and y in our system. So like this could be written as a times x plus b times y equals c. And here a, b, and c are numbers. X and y are our variables. So maybe I'll change those to be a different color. Another way to write this is y, and I'll put my x in blue again, y and x in blue equals mx plus b. This is called the slope-intercept form. And the one above it is called standard form. Most of the work we're going to be doing will be in this slope-intercept form. And so I want to cover a little bit more about it, what's going on with it. We've got two things that the y and the x are related to any point on the line. The m and the b are going to remain the same where the y and x change. So m stands for, I don't know why they use m since it's not in the word. M is the slope. You might have learned it as rise over run. It's a change in y values over a change in x values. And sometimes they say change as a triangle. Oops. So that's another way that they write it. So let's look at what the change is on this line. Let me address B real quick too. B is my y-intercept. This is where the point on the line where x equals 0. And that means it's where it intersects the vertical white line, or intersects our y-axis. So the lines that are the 0 lines, this is called the x-axis. And the vertical line is called the y-axis. So if I look at our line, I'll put my y and my x here. Where it intercepts this y-axis, where it crosses, is right here. And that is down 1, 2, 3. So here b equals -3. And so that's what I'll put. I don't put plus -3, I'll just say -3. And then to look at the slope, it's how far I go up as I go to the right. So I'm going up 1, 2, 3. That's my rise. And my run is how far right I go. 1, 2, 3, 4. My run is 4. So my slope is 3/4. That's one way to look at how slope works. It's an important way. It's the rise over the run. How much we go as we move. Notice that this slope is positive, and our line goes upwards from left to right. If the line goes downwards from left to right, downwards, the slope will be negative. And we'll look at an example of that in a second. So that is one way to count the slope, and it doesn't matter which 2 points you use on the line to do it, as long as you count how much you're going up and how much you're going right, or how much you're going down or how much you're going left, depending on which direction you're going. There's a couple ways of looking at it. So I could look at this. I did this going upwards from the left point, but if I started at the right point, I could look at this as going down 3. So rise would be -3. And my run, I'm going left, not to the right. I'm going left 4, so my run is -4. And if I do -3 over -4, the two negatives cancel. And I'm again left with positive 3/4. So it doesn't matter which direction you go, as long as you recognize down or left is negative and up or right is positive. So that line I have right there, y equals 3/4 x minus 3. Another way to look at m. So this is a good way to look at it in terms of stats. The stats viewpoint. For every increase, every time we increase x by 1, we increase y by m. So for us, if x goes up 1, y goes up 3/4. And I'm going to go back and look at that line and show you that again. We'll take a look at what's going on there and how that's working. So let's go up, look at it. All right, so I'm going to start. Let's see, what color do I want to use? I'll use white. So I'm starting here, and as I go right 1, that's my pencil version. I don't like that. I go right 1, I go up 3/4. So that's a 3/4 increase. I didn't go up a full number line. A full number line would have gotten me here, and I didn't get up to that. I only got up to there, and if this was on a better graph, you'd be able to see that's an increase of 3/4. From here, if I go right 1, I go up another 3/4, which should put me right around there in the middle of that. So these were our original lines. I go up another 1, or I go right another 1, I go up 3/4 again, and my number line is starting to look lame. It should have been like that. So my numbers don't look good. My line doesn't look good, but that's the idea. Rather than looking at how far we change over a bunch of, like a long leap across the line, we can also look at it as just a change in one step to the right and how far up or down y goes. Load up a good example before I talk about the next word. Okay. Let me come over here and let's bring up my Mathlab. I want to go into StatCrunch. And I want to bring up a specific example that we're going to use. It's so I'm going to use data sets from my textbook. And we're going to chapter 4, 4.2, problem number 7. All right, I'll go over a little bit more of what's going on with 4.2 in a second. But it's nice to have that data up. Let me, nope, I don't want to do that. I want to have that like that. And I want to have my remote desktop like that. So let's do some side-by-side magic if we can. That's not what I want. Where is it? There it is. Make this a little bit wider. Okay, so where does this come into play in statistics? A couple things we'll look at. We're going to look at scatter plots over the next couple sections. We're going to look at the QQ plot. And we're going to look at simple linear regression. So to do the scatter plot, I'm going to do it right now. This isn't where I was planning on talking about it, but scatter plots is graph and then scatter plot. And when we click on it, it'll tell us what it wants. It wants our X variable and our Y variable. Oops. Damn it. So I am going to make my X variable the length and the Y variable is the weight. We haven't talked about it more than that, but I just want to show you what's kind of going on. This is kind of all over the place. The dots are everywhere. It's not actually showing the scatter plot. So I'm going to edit it. And what we want to do is we want it to display lines. And is it going to, oh, and then we're going to have it do the best fit line. You don't need the best fit line, but it can help. We will be using the best fit line later. And that's not the line. That looks terrible. I did not want lines right there. So we'll go back to points. So the data is kind of going all over the place. So let's take a look at what we're seeing here. Because like in all cases in statistics, data never makes a straight line in stats. Never, ever, ever makes a perfectly straight line. But as we can see here, in some cases, like as it's going from left to right, I mean, the dots are kind of all over, but the dot on the right is pretty high. And the dots on the, there's dots on the left that are kind of low, and there's dots in the middle that are kind of like that way. So this is, and it's got, I've got this red line. I'll draw that on there. This is called the, totally not what I wanted. There we go. Let's get it red. It's called the best fit line. We'll talk about that more in a little bit. The real issue here is what the dots look like they're doing. They're not in a straight line, but as it, if it goes upwards from left to right, this is called positive, or yeah, positive linear correlation. Well, yes, positive linear correlation. Actually, I'm going to remove the linear for now, because we're going to show you how you can find out if it's linear or not. So let's just call it positive correlation for now. And it's correlation between the X variable and Y. In terms of stats, the way we talked to this is back in like chapter 1 or 2. X is our explanatory variable. It's explaining why, what happens to Y, and why it happens. Y is our response variable. There's a change that's happening as X changes, Y is changing. So X changing causes Y to change. We could have it where our dots go downward from left to right. And if we put our best fit line on there, it might be something like that. And line goes down from left to right. This is negative correlation. Okay. Now, we see this graph right here, and the dots are kind of all over the place. Like our graph has a dot way down here that's super low, couple dots here. So they're like some of them are way off, and I know that. There are circumstances where we could have our yellow dots be much closer to a straight line. Not perfect, but much closer. So these dots are closer to the straight line than above. This means X and Y have a stronger correlation. And so this is a math course. We measure that strength of the correlation how strong that correlation is by something called the correlation coefficient. So this was my length right here. And these were my weight. We'll look at that more in a second, but I just want to have it there. Because I want you to remind you, this is representing data. Now I'm going to throw the equation at you and you're going to go, what the fuck? Oh, hell no, Mr. Jones. And if you may not say it, but if you don't think it, you're a sick person. You should get some therapy. Because I look at it and that's my thought. If someone asked me to do this equation and solve it, I would be all hell to the motherfucking no. We use R, little r, or big R for the correlation coefficient. StatCrunch uses big R, but often we use little r. So the equation for R is I'm going to write it out before I explain to you what it is. And then we have this all over n minus 1. That is the equation. Thankfully, we're not going to use it. I'll show you how to find it by the computer. But what it's doing, though, is it's using these values. The x and the y that don't have a bar above them are for the actual data. X bar and Y bar, we've talked about these before. They mean what they've meaned in the past. This is the mean of X and Y respectively. And we've used S before, but I've never put a letter behind it. S was standard deviation. So S with the little x is standard deviation of X. S with the little y is standard deviation of Y. And N is our sample size. And since we are refreshing for your midterm, why don't we just remind you how to get those? If I want to get the mean and standard deviation of a data set, we can go stats, summary stats, columns. We can select our columns. And then I want N, I want mean, and I want standard deviation. So for the problem, the numbers we're about to look at for 4.2.7, our data set, N is 12. We've got X bar is 142.875. Y bar is 99.583, and the threes keep going. Standard deviation of X is that 11.632879, and the standard deviation of Y is 27.998241. So to use this formula, you really kind of got to go through and subtract the mean each time, divide, multiply. This is a giant tedious pain in the ass. It is a giant tedious pain in the ass. But we'll talk about how you can get it in a second. I want to talk about some other types of correlation now, just to point out that it doesn't always look like this. So other types of correlation. Actually, let's get all three on. I want to do three. So I'll just make this a little bit narrower. So I could have dots that are going up for a while and then they start going down. I could have dots that are going up and then they shift to go downward and then they go back up again. Or this could be the other way. I mean, it could go where they go down, like here, it could go down and then up. But that's just a different form of having it change. And our other option is they could just literally be like all over the place. So these are types of nonlinear correlation. Nonlinear correlation. Because when I make that red line, the best fit line, it's no longer straight. Here I would be following a curve. Here it's following a curve. So this might be quadratic or squared correlation. Oops. Like y equals x squared or negative x squared. This could be like cubic correlation. Y equals x cubed or negative x cubed if it's going upside down. And then here, can I make a line? I don't really know. So like the data may not be correlated at all. No correlation between X and Y. So for our class, we are going to focus on linear correlation. Linear correlation only. And we have a couple ways of getting that R value. So linear correlation is R or big R. Some options we will use is stats, summary stats, correlation. We can also look at stats, regression, simple linear. That top one looks funny. Is that a thing? Yeah, correlation. So stats, summary stats, correlation. We're going to do the correlation between those two lines. And we're just going to click compute. And it says the correlation between total length and, so I'll draw a little line here. This is giving us, when we do it for our problem here, 4.2.7, it says R equals 0.703-90318. Let's see what stats, regression, simple linear gives us. We need to tell it what it's looking for, which one's X and which one's Y. And I think that might be good for now. And notice it gives us some more information. I can see my R here. It's the same value, right? See the same value there and there. It also gives me this right here. So simple linear regression option. Hello, clicky, clicky. This gives us the same R. But it also gives us this equation right here. It says weight in kilograms equals negative 142.47092 plus 1.69. That is so, I'm saying different numbers than I'm writing down. Should I do that on the other ones? 47092. And then I got 1.694168 total length centimeters. Now I told it that total length was X. These were my X values. And I told it this was my Y values. And maybe if I round those numbers a little bit, I'm getting Y equals negative 142.47 plus 1.69X. If I get rid of the words and put Y and X back in. And now we've seen, and we talked about this earlier, I've got a number multiplying by X and then something added to it or subtracted to it. If I put the X part first, this looks like our Y equals mx plus b. And it is. So it's telling me the slope of that line is 1.69 and my y-intercept is negative 142.47. We'll look at a little bit more in a little bit, just showing you what kind of information this stuff yields. And so, like, how can we do, like, the correlation coefficient? What does it mean? Like, is the 0.703 good enough? Like, is it big enough to say it's a straight line or close to a straight line? So, like, how do we decide with our number? With our correlation coefficient R, if it's close enough to a straight line. To be called linear. Because that's what we care about. Linear, it's got the word line right in it. I did not update the pink. There we go. So I'm going to show you how it works, but maybe we should talk about R and what it means. Like, what's going on with values of R? Let's talk about the properties of R. So first thing, R is always between 1 and -1. Which means it's always a decimal, 0 point something. Might be positive, might be negative, but it's always 0 point something. The next two are kind of related. The closer R is to -1, the stronger the evidence of negative linear correlation. Or another way of thinking about correlation is association. How are they associated? If correlate is not a word that you like very much. And if R equals exactly -1, it's perfect negative correlation. And that's the scenario where the dots all make a perfect straight line. Like a perfect line. It doesn't happen. Like it might happen 1 in a million times. It's not common. If we go look at it going the other way, though, the closer R is to +1. I don't know why I wrote positive, spelled it out. The closer R is +1, the stronger the evidence of positive association or correlation. And again, R equal to +1 is or perfect positive. Correlation. And I wrote that in pink up there, so I'll just put a little pink box around it here for the positive one. So what about when R is not close to -1 or +1? Well, that means it's closer to the middle, 0. That's not what I want. When R is close to 0, there is little to no evidence of a linear relationship. But it might have some other form of correlation. And those were the examples we showed up above, like quadratic or cubic. And again, we're not focusing on those in this class, so we're just concerned whether it's linear or not. It's important to know that R is unitless, which means it's just a number. It's not like R frisbees. It's just a number. And R is affected by outliers. Which means it's not resistant. And we were so used to seeing our outliers being to the left or the right. But if I look here at that graph we had, like we might be able to call that an outlier. Oh shit. Let's see, annotate. I might be able to call that one an outlier. It's a long ways away from the line. So that might be an outlier. It just all depends. So what do we do with this R when we have it? What to do with R? So some problems will give you this in the notes, but we want to compare R to the critical value. Critical value. And I am going to call critical value CV because I'm going to say it a lot this semester. We're going to compare it to the critical value. And it's on a table and it requires knowing N. Okay. Where can we find the table if it doesn't show up in the problem? If it doesn't show up in the problem, we actually have a copy in our lecture notes. Let me get back over to our class. Nope, that's not. There we go. No, actually I wanted Canvas. So let me get out of that course, come over to our stats course. And, oh wait, I need to blow this up. I don't know where it is when I'm looking at it that way. We're gonna go to Files. Why is it? Am I in the wrong course? What the hell is that? What? 15,972? What is it clicking on? It's just picking random courses. There we go. Files. We're going to come over to useful handouts. And we're going to go to stats. And we're going to go to stats, formulas, and tables. This actually has a lot of the formulas we've used during this semester on it. Here's our z-score formula. Here's our interquartile range and finding the lower and upper fences. Talks about correlation right there. It's got our probability equations right here. This might be a little handy thing to look at to remind yourself what's going on. Where the table is, though, we want to come down, and I want to say it's on the 5th page or so. You get to the tables. Table 2, let's see. Critical values for correlation coefficient. So I had n equals 12 for the set we've got, and that's 0.56. I'm going to write that down in my data set real quick. So this is from our files section. You're going files, useful handouts. Let me write down the number first. N equals 0.576. It's table number 2. We do use the normal probability plots later on when we're doing that normal curve. Do not use these. This is the old standard deviation way of doing it before StatCrunch. It's a pain in the ass. Don't do that. So we're going to use critical values for correlation coefficient. And again, it was in files. You click on useful handouts. Click on useful handouts. Then you click on stats. And that's right there. StatCrunch Tech Help might be good. You're going to be doing the midterm, and if you're trying to do this all by hand, you're going to have a really crappy midterm. So knowing what to do in StatCrunch can help. So we get that critical value, and what do we do with it? There we go. So what do we do with our useful handouts? I was writing it down. Handouts, stats, and then stats, formulas, and tables document. So what we're going to do is we take R, and we're actually going to take the absolute value of R, which means in terms of our purposes, make R positive for our comparison. So if R, or absolute value of R, is greater than a critical value, a linear correlation exists, or a linear relation exists. And then that's absolute value of R. If that's true, if R without the absolute value is positive or greater than 0, it's positive linear correlation. Am I even recording right now? Yep, I am. Good. Thank God. Couldn't remember. And if R is less than 0 or R is negative, it's negative linear correlation. Now, most homework problems provide a link to that critical value table. You just need N to find it, your critical value. I think I'm going to pause the chapter 4 lesson here. We'll continue with lesson or chapter 4 after the midterm. And we'll do more stuff with this. We'll use the critical value, and we'll follow with that example further there. We'll continue with chapter 4 after the midterm. So what kinds of things do we need for the midterm? Let's just do a quick review. Let me pause, make sure everyone's on the same page. How you guys doing so far? Okay. I'm gonna go back to that table actually, because it says a list of chapters and that might be helpful. So chapter 1, we talked about terminology. We talked about discrete values. These were countable, although maybe really large. Like the amount of money Elon Musk has. Elon Musk. Is technically countable. In fact, his bank keeps count of it quite well, keeps track of it. How much money do you have? It adds and subtracts to it as necessary. That was discrete values. Then we had continuous values or variables. These are things that had to be measured. Time, length, any form of length, width, height, stuff like that. So length / distance is a way of thinking of it. You can think about weight, things like that. Then in chapter 2, we hit up relative frequency or frequency and relative frequency. And we also did some other like graphs, like pie charts and shit like that. And in this area was also histograms. So frequency was just how many of each item. Let's see, participation went, Giselle had to leave. She was here though. I'm going to count her for this example. So if I broke my students up into groups, students that showed up and students that did not, attendance equaled 3. Non-attendance is like 95. Which is fine. Again, this is not a class that you have to show up for. It's asynchronous. So those are examples of frequency. Relative frequency was, we made a ratio with these numbers over the total. A ratio or a fraction with these numbers over the total. So if I add up 3 and 95, I get 98. My attendance frequency is 3/98. My non-attendance is 95/98. And we could turn this into a decimal if we wanted to. In this section, like we had our histograms. I'm just drawing a few. So if the big part of the graph was to the left, the mound was to the left, and it made a curve going like that, this was skewed right. And if we had the hump on the right and the long tail went to the left, this is skewed left. So this is the tail. Both sides have a tail, but the left side's tail is really short. And so whichever tail has really a lot longer than the rest is the side of skews. And then if we had a nice little shape where there was a mound in the middle and it was like the tails were about the same on either side, this was bell-shaped. We had chapter 3. We started looking at numerical summaries of data. That's our good old mean, median, mode. We also had standard deviation. This is where our quartiles showed up and our interquartile range. IQR. The 5 quartiles we use for the 5-number summary. Is min, first quartile, median, third quartile, and max. I frequently called this Q1. I changed it to pink. Why is it not doing pink? There's a delay. Called that Q3. This is like Q4, Q2, and Q0. But those have names, mean, median, and max. All of this stuff was stuff you could find under stats, summary stats, columns. You just had to tell it what you were going to pick. And if you want to look at the formulas, come back and look at the stats and formulas table. Like it's got the formula for mean and population, or sample mean, sample population. It's got standard deviation. It talks about range. It's got the interquartile range down here, the 5-number summary, the fences. This is when we started looking at the empirical rule. This was our 68%, 95%, and 99.7%. We've got the mean in the middle, and we go out 1 deviation in either direction. This region has 68% of the data. If I go out another deviation either direction, now we're 2 deviations out.
Professor Jones,
Yeah,
half of the screen is being covered by the other site.
I see that. Thank you. Thank you for saying that. As soon as you spoke, I looked up and saw it. I'll pause a second. So between these two was 95%. And finally, when we go out 3, it does go out more, but this is where it, after that, it starts getting so minuscule that it doesn't do a lot of damage. The values between this range and this range covered 99.7% of the data. We saw when we were looking at chapter 7, the numerical or the normal graph, that it doesn't match up perfectly, but it's the rule of thumb we use when we're doing deviation, or like perfect deviations, 1, 2, or 3. Let me shrink that down. If I wanted to, I didn't mention earlier, but we want to do graphs, you can do bar plot. If you've got data, use it. I'll just do one. That's not very good data. This is not like good data to do a histogram stuff on. A histogram is also over here, and you can do binning. Let's go back and look at that list of stuff. Chapter 4 is not on the midterm, so we're not going to talk about it right now. Let's talk about chapter 5. This was our probability section. Remember, we had probability of E or F is the probability of E plus the probability of F minus the probability of both. If the two things we're studying, if E and F are independent, or they don't affect each other, like 2 dice being thrown, this value ends up equaling 0. And you're just stuck with the probability of E or F is the plus. So, or leads to addition. when we were looking at the probability of E and F, like both events had to happen, this is where we multiplied. So, and turns to multiplication. Worth remembering. We talked about doing the probability of F given E. Could you write that any bigger, Mr. Jones? Jesus. I got and the multiplying symbol up there. Probability of F given E. There's a formula for this. Probability of F given E equals the probability of both divided by the probability of E. This is when we had probabilities. We also did a version where we had the number of E and F over the number of E. So we use this one when you have probabilities with probabilities. And we use this one with data counts. One with actual data. How do I want to say the next part? Oh, I should say more about this. If probability of F given E is the same thing as just the probability of F, then E and F are independent. That looks like crap. Then E and F are independent. Now, another way to do the probability of F given E, that's when you had numbers, but when you're doing like actual calculations for some stuff, like another example of this is, what is the probability of drawing a spade? From a deck of cards, playing cards, they're called. If we've already drawn out the ace, king, and jack of spades. Now you can go through and use the formula probability of F given ace, king, queen, and jack are out and use that formula up above, or you could just reason it out. Each suit has 13 cards. If I've drawn ace, king, and jack are out, I have 10 left. And the total in the deck has gone from 52 down to 49. Then my probability of getting a spade, given that the ace, king, and jack have been drawn, that's my spade symbol, is I've got 10 and I've got 49, 10 over 49. And I didn't use the formula, I just reasoned out what was left. Also in this section, we had NPR and NCR. NPR was n factorial over n minus r factorial. You're probably just using what was on your keyboard or your calculator. NCR has the exact same thing, but it also has r factorial on the bottom. NCR is for combinatorials or combinations. Order doesn't matter. I don't care if I'm the 5th person or the first person to be drawn from a jackpot drawing if everyone gets the same prize. As long as I win a prize, I'm happy. If the order does matter, like first prize, first person or the top prize is way better, you know, like $1 million, and then second place is like a car, I'd much rather have the $1 million. Here, order does matter, and that's NPR, order matters. P is for permutation. And I write this in caps. And it's got the letters of matter right in it, M-A-T-T-E-R. So order matters in permutation. How you guys doing? This is our recap of the semester. What do we got here? What else we got here? Chapter 6, does it have our formulas that we're going to write down? It looks like it does. That's handy. It's all in one spot. Chapter 6, we did our discrete variables. And just the general mean was the sum of x times p of x. This is what we did when we were doing probability models. And to verify those probability models, don't forget they had to be between 0 and 1. And they had to add to 1 for probability models. It actually gives you the formula for the standard deviation, but it's a pain in the butt. Did we even do that? I don't think I made you guys do standard deviation. No, I didn't even show you the formula. I'm not going to show it to you now. Where did we do this in StatCrunch? This was in, let's go look at it. Stats, calculators, custom. These are not values and weights, so I don't really want to do it here. But yeah, you know what? I am going to do it simply to show you that what it spits out. Like these are bad, but it will give you the mean and it will give you standard deviation here. So the spit out for this calculator does give you mean and standard deviation. Then we had our binomial. Binomial distribution. And what did it require? There were some requirements. There had to be a fixed number of trials. The trials had to be independent of each other. One toss of the dice does not affect the next toss. There could only be 2 outcomes. And we tend to call them success or not. Or not a success. And remember, depending on who you are, success might be something grim. Like I don't know, the life insurance policy. I don't. Point is, success or not depends on which side you're looking at. Then we also had one other thing. Oh, I need to say continue. Probabilities can't change between, probability cannot change between trials. If we had that, the probability X was n choose X. Then we had P to the X power. And then we had 1 minus P to the n minus X power. Where X was the number of successes. We didn't want to do that by hand though, so we did stats, calculators, binomial. Here, this, you didn't need the data set. So that's worth pointing out. Stats are the custom calculator. You need data or need stuff in StatCrunch, in a table in StatCrunch. For the binomial calculator, all we need is N, P, and X. Don't forget the signs. Your less than, greater than, less than or equal to, greater than or equal to. And don't forget about the between. The between, you don't have the option of less than or greater than. You have to have the equals part with it. So you might have to custom choose your numbers so that that works when you do the between. And we also had the Poisson distribution. Oh, maybe we should talk about what those values are. What's our mean and what's our standard deviation? The mean for a binomial is n times p. Standard deviation for binomial is n times p times 1 minus p square root. As we can see on this table right here. Mean and standard deviation of a binomial. Then we had our Poisson distributions. And the problem should say Poisson when you get to it. We had mu equaled lambda t. And sigma is the square root of mu, or the square root of lambda t. Lambda was the rate, and t was the units measured, usually time. And for that, we did stats, calculators, Poisson. I keep writing it wrong. POI, fuck me, 3 times in a row. Now I'm just erasing it. Quit rushing it. POISSON. There you just need the mean. Needs mean and X. If they asked you, how do we pick N? For like the binomial, the Poisson, or anything like that, given a certain, for a given P, we had N times P times 1 minus P had to be greater than or equal to 10 and solve for N. Finally, chapter 7. Does say anything useful over here in chapter 7? Nope, they just talk about the z-score and finding the score. Was on continuous distributions. And this was our normal calculator, normal distribution. You would have a mu and a sigma, or mean and standard deviation. And you could find and Z will be, now Z is the number of standard deviations. And X is our value. We had X equals mu plus Z sigma. We saw this on the graph a lot. Mu plus 1 sigma. We saw it on the graph a lot. But it didn't have to be a whole number like 1, 2, or 3. It could have been in between. So you could always calculate X if you knew those values. Normally, though, we wanted to find the Z-score. And that's just solving that equation for Z. Is X minus mu over sigma. And what this does is it takes the normal distribution and turns it into the standard normal distribution. And now the mean in this case is always fixed. The mean is 0. And I did not write 0. I wrote standard deviation. And the standard deviation is 1. So StatCrunch is stats calculators normal. And it defaults to standard normal. Mu is 0 and standard deviation is 1. So you had a lot of stuff. I would definitely, pro tips for the midterm. Midterm is available 12:01 a.m. on Wednesday through 11:59 p.m. on Sunday. But you have a fixed amount of time. I think it's 2.5 hours. Oops. Once you start, you have to finish. I think it's 2.5 hours. It says it in my syllabus. We can go look at it in a second. There is a practice midterm up. Take it. Practice. It'll show you what I expect on the test. Let's go back and look at it. I'm probably gonna have to re-log in, probably log me out. It did not log me out. Look at that. Beautiful. Midterm review is due, which means it's available. Through Tuesday night at 11:59 p.m. Then it's no longer available because the test has started. Make sure you're well rested, fed. Maybe go to the bathroom first. Like, because you can get up and walk away from your keyboard to go to the bathroom. But once you've started the test, you're eating into your time, and that's a bad idea. It says 150 minutes there, so it is 2.5 hours. Make sure to read the problem. The whole problem thoroughly and slowly. And reread it before you answer. To make sure you're actually answering the question you thought you were. Like, it's easy to get started doing some work and then just all of a sudden, nope, that's not what I was supposed to be doing. And like you done forgot, you had to find something along the way and you got the wrong thing. Double check for decimal places. And double check your rounding. As long as you have not submitted the exam at the end, you can always click back to the first question. Like if you find that you got it done early and you got some extra time, take a break, click back to the beginning. Don't close it. Click back to the beginning. And then just double check your answers. If you've been writing them down, you can make sure you answered what you've been doing along the way. Okay. And that's it. Any questions? All right. We will call that a wrap then. I'll stop recording and
Have a good day, Professor Jones.